Okay, good morning. This is Statics ENGR 214 ampersand Bellingham Technical College Winter 2020, and we'll be discussing centroid and center of mass today, mainly centroid, and then we will multiply our integrals by a density function, a continuous density function, to get center of mass pretty much the same way we get centroid. So it's a twofer. This is the last main topic of the quarter, and we'll complete our study of statics for this winter quarter. So this will be obviously one of the big topics on our final exam at the end of this week. So hopefully this will help you all prepare and get this concept locked into your mind. We are going to be using pretty much an exclusively calculus-based approach for this. This is necessary when we're dealing with general bodies, any kind of shape or size. We've used calculus for lots of different topics: capstan equation, derivation, our shear and bending moments. So we're going to continue to leverage the idea of integrals and adding up a small volume or area or mass element over the limits of integration, expressing the extent of the size of something that we are looking for the centroid of. So just a verbal definition for those of you for whom physics has been a while back. Centroid is otherwise known as the geometric center, and the center of mass is effectively the mass center. If you're looking at something in a gravity field, the center of mass is the point about which, in any orthogonal direction, the body would balance. So the gravitational forces acting on the mass on either side of that balance point are the same, and so the object would kind of stay balanced on a single point. And so we will have a centroid and a center of mass, which we can define for each orthogonal direction. So you'll have an x centroid, a y centroid, a z centroid, and of course the same thing for the corresponding center of mass when we roll in our density function. So we're going to take a step back now and just do a really general definition. We're going to kind of enter the world of the abstract just a bit, but that's going to give us a good platform going forward to generalize our definition, and then we can drop in any volume, any length, any area, and be pretty confident about knowing what we're doing in terms of calculating centroid. So general definition, we're going to take any body Q. Okay, so this is a body Q, and it's a blob. It's hanging out there, and it's occupying a region R. So the region is defining the boundary. So this is a spatial boundary. Now Q can be a line, it can be 1D, it could be an area, so the boundary would be a circumference, or it could be a volume. So the regional boundary R would be a surface. Okay? And there's some point somewhere in this body Q within this region R that is the centroid. Okay? So if I define a coordinate system origin, a reference point O out here, so this would be maybe like x, y, z all equals 0, some reference location, and I did a radius vector from that location to C. Okay, so I'm defining R, O to C. That would have a relationship to the sum total of all the R's to every tiny infinitesimally small bit of that body Q integrated over region R, which will make sure I add up every bit of Q. So mathematically I can say that that's equal to the total area, length, or volume Q times the length of the radius R from 0 to C, to our point C. That's going to be the same thing as adding up the radius from our origin to every point in the body, integrated over the whole body. So that's literally how we back out the definition of C. It's the location such that the radius from some reference point to that location times the total length, area, or volume of the body in question is equal to the sum of the radii from that same reference point to every bit of that body and then summing up the product of each of those individual radii to those bits of body over the whole body. So here you kind of got the full chunk to an average position equaling the sum of the specific position times every little bit of body. So it's a bit of an averaging kind of concept. So if we know the volume or length or area of the body, our position to C defines the centroid. And we can just divide this other term by R, and the radius from some reference point to C would effectively be our X or Y or Z or R theta or phi location of the centroid. So the centroid is defined as a location, in this case a radius vector from the origin to some point on the body or some point within the body. You could have a ring, so the centroid is at the center of the ring. Okay, so if we impose a rectangular coordinate system, which we're going to be using most of the time, we can take this general expression here and drop in X, Y, and Z. So again, we've got our total body volume, area, or length, because we could be talking about X, Y, or Z, and then we could define an X centroid, and then that would be equal to the integral of the X location, and that's just X reference to an X equals 0, so it's a radius from X equals 0 to X equals some X, dq, which could be like a dx, dy, ds for a path length, or a dA if we have a two-dimensional body, or a dv if we have a three-dimensional. So it's some X location, any X location somewhere on the body. So this is the X location of this little bit of body. Same thing with the Y. We can take, again, the entire length or area or volume times the Y centroid location is equal to the Y location versus some reference point of that little bit of the body that is at that Y location. And then we add it up over all of the bits. Same thing with the Z. So dimensionally, if it's 1D, you'll just have an X or a Y or Z. If it's 2D, you'll have two of the above. If it's 3D, you'll be able to define a centroid in each one of the three orthogonal directions. Okay. So just making sure we caught everything. If Q is an area or a surface or a volume, dq will be expressed in terms of one coordinate axis and an area or a volume. And you could express this in terms of an area or volume generating function. So this brings up different ways. Now that we're going to look at actually putting this into practice, we can define if we just have a length, like a wire in some shape, and we want to look at the X centroid or Y centroid of the wire, we'll be integrating in just one dimension. So there'll be a dx or a dy, a ds in terms of some X or Y function. But if we have an area, we're going to end up with a dx and a dy to basically give us a dA. So for those of you who are studying integral calculus, you know that you can integrate with respect to x or with respect to y and basically add up slices of a function between limits. And you can express invertible functions in terms of x or y. You know, the independent or dependent variable, you can switch them in a lot of cases. And so that gives us some options on how to execute this, because for a continuous function that doesn't have a defined shape, we're probably going to have to do an integral just to get q. Then we're definitely going to have to use integration to do x dq, y dq, or z dq. So sooner or later we're going to be looking at how do we integrate functions over defined limits to actually evaluate our centroids. We're going to have to get our total area or volume or length, and then we're going to have to evaluate the integral of the distance to each bit of area, volume, or length. So we're going to take a little step back here in one example, and we're going to look at our different options for integration. And this is basically, we're going to kind of do a bit of a math review. So we're going to look at a really simple function. It's a parabola with just one term, y equals x squared. Or if you wanted to look at it from the point of view of x being the dependent variable and y being the independent variable, this same curve could be defined in terms of y, and we could say that x, any x location, is equal to the square root of y. These are equivalent functions, so we can invert. And so we'll use that to give us different options for integration and just prove that there's more than one way to do this. If we wanted to use a double integral, what we could envision that we would be doing, and this is an example for just getting the total area, so that's getting this part of the centroid, say. I'm going to define the area under y equals x squared, going from x equals 0 to x1, or I could look at the area under x equals square root of y from y equals 0 to y equals y1. So I can look at different limits of integration. So I can look at that in terms of adding up slices and squares. So here's one way of expressing that area. I can integrate in the x direction, dx, from the function, which in terms of x, from x's point of view, is the square root of y, to this upper limit, x1. And what that'll do is this will create this horizontal strip. So for every y position, I'm gonna make a horizontal strip. So once I have this horizontal strip defined, then I'm going to integrate with respect to y and add up all the strips from y equals 0 to my upper y limit. And that would give me the total area. And the nice thing about defining our area this way is if we wanted to define the x or y centroid, all we would have to do is drop in an x term here or a y term right there, add a little bit to our integral, and then we would have the second side of the equation. We would have already had a, and then we just divide across and would immediately have our x bar or y bar. So we'll go ahead and do that. We've already got a right here. So let's write the expression for the x centroid using our definition here. So we'll say a times the x centroid is equal to the integral of x dA. Okay? Well, we've already defined dA here. So x dA is just x inserted in this integral. Okay? We knew the same thing with y. A times the y centroid, or y bar, equals y times dA. Well, we've already got dA again. Now we pop in a y. So if we integrated these two expressions, and remembering your rules of integration for multiple variables, remember, just like taking the derivative, if you're integrating something with respect to one variable, you treat all the other variables as if they're constants, and you integrate from the inside out. So in this case, I would integrate x with respect to y, and then I'd pop in these two limits of integration, include that as the function being integrated, and then I'd take whatever that function ends up being and integrate that with respect to x over these limits. And of course, just as a hint, if I'm integrating x with respect to y, x might as well be a constant like 5, so I would get xy. Just a quick review. So this is one way to work a centroid evaluation of a continuous function. I didn't need to necessarily rely on the fact that it was invertible except to get the limits of integration, because I had to know what the function was called with respect to either potential independent variable to know where to start integrating. So in this case, the function inversion ended up in the limits of integration. But otherwise, it's pretty straightforward. We add up little boxes to make a strip, and then we add up strips to make an entire area. And then of course if you needed to make up a volume, then you could just integrate over the limits in the other orthogonal direction. So something else to remember is if you, for whatever reason, don't want to use a double integral, you can always express either one of these, dx, dy, directly as a dA in terms of one or another function. So I can always say that my area is equal to, a differential area unit. I could start with an entire strip. A double integral starts with this little square, adds up those squares to make a strip, and then adds up strips. I can define a strip. So I can define a vertical strip with this term. I can say, okay, the area of this vertical strip that I'm kind of outlining with my little grabber cursor is equal to the height of that strip, which is the y at the point right in the middle, because I'm going to make it infinitesimally small, times the width, which is dx. So there's one way of writing dA. I could also write it in terms of this horizontal strip. So I could say it's the x width, which is the function value to this x1 limit over here. So it would be x1 minus the function value actually. So that's the x width times dy, which is the thickness in this direction. So that's another way of doing it. And guess what? You get the same thing no matter what you do. And we can prove it. We can actually drop in y dx. And what is y? It's x squared. Or we can do x dy. And in this case, the x strip width was our x1 minus the function value, which is square root of y. And if we integrate either one of these, we get the same. And if we perform the double integral in either order, these all give the same value. They all give you this same area. So we have multiple different ways to approach a problem. It's just going to be a matter of whatever is easier. So just kind of use some definitions of functions and definitions of integrals to set the stage to make these centroid calculations a little easier. Having done that, we're going to go ahead and actually evaluate the area using our limits, and I chose, just because I'm familiar with integrating with x as being my independent variable, I chose to integrate this one and calculate area that way. So I integrated x squared dx from x equals 0 to x equals x1. So I integrated this way from 0 to x1, popped in my limits of integration, and I got 1/3 times this x1 limit, which is some number, cubed. So that's my area A. And if I were looking up here in the general definition, that's effectively Q. So now if I want to get the x and y centroid, I need to, I have my A. Now I need to get my integral of x dA and my integral of y dA. And I'll divide either one of those by this term, and then I'll have my x bar and y bar. So it's two separate operations to get that. And just to be versatile, I've also evaluated area using the other methods and shown that it comes out to be the same thing. So all four give you the same thing. So that was a bit of an exercise, just having fun with math. But getting down to centroid here. So now I'm going to use my double integral, my dA from the other page, and I'm going to evaluate effectively x dA using a double integral. So I have my x, and so I'm going to integrate y from 0 to the function value for any y, which is x squared. And then I'm going to take that result and I'm going to integrate from over the relevant x limits, which is 0 to my x1. So my first expression is going to give me x times y, basically evaluated between 0 and x squared. So you can see I have my definite integral in the square brackets with my x, which was acting like a constant, to my dy integration. So I kicked out a y. So if x had been 5, it would have been like 5y, because x acts like a constant. because I'm integrating with respect to y. So I have xy evaluated between 0 and x squared. Okay, well, 0 just makes a 0, and so you end up with the x squared dropping in for y times x, which leaves me with x to the third. So I have x to the third, which is the result of my y integration. So now I'm going to integrate with respect to x between 0 and x1. Well, x to the third dx integral is easy. It's a polynomial. It's 1/4 x to the fourth, evaluated between 0 and x1. I drop in my limits of integration, and I get x1, which was this limit here, this value where I'm integrating to. It's defining one boundary of the function area that for which I'm getting the centroid. So the bigger that x1 is, the further to the right my centroid is going to shift. So I get x1 to the fourth over 4 coming out of my x dA integral. So the total area times the x centroid is equal to this. Okay, great. I know what the total area is. It's this. So if I take this and I divide that, then I have the centroid. So I do that and I get 3/4 times x1. So basically, the x centroid is linearly related in this case to where I define this x1. The further over I define x1, the further over the x centroid will be, which, you know, doesn't seem surprising. So we can do the same thing with the y centroid. So I have the same area times y bar, and this time I'm going to integrate y dx dy. And we're going to have different limits of integration because now we've defined that horizontal strip instead of the vertical strip, but otherwise the procedure is the same. You can step through the math, and we find that we get this expression just cranking through the math for the y centroid, and we have it in terms of both the x1 and the y1 limits. So we have it. So we've now expressed the y centroid in terms of this y level and this x level, both of which correspond to that particular point. So if we want it in terms of just x1 or just y1, we substitute in what x1 and y1 are related to one another, which is just to the 1/2. So we're using our function inversion there, and we pop that in. Sorry for the screen going back and forth. We just do a substitution in this case, and we get our y bar in terms of the y limit. So if our upper limit here that defined our centroid area of interest is y1, y bar is going to be about a third of the way up, just shy of a third of the way up. So x bar was at 3/4 of the way from 0 to x1, and y bar is at about 1/3, just shy of 1/3 of the way from 0 to y1. So I call that adventures in Cartesian integration. But you've got a lot of options for integrating, but all of it ends up effectively being evaluation of this expression and this expression. So it's however you want it, and remembering you need a continuous function to integrate. Okay, let's look at a case where we have to define a little bit more creative dA. We've got a semicircle defined here, and we've plopped it down at the origin of a Cartesian coordinate system, and we want to know the x bar and the y bar for the semicircular area. So this is all filled in. This isn't a wire arc. This is like a half disc where it's down on the origin in this configuration. So again, we're going to be looking for the area times x bar is going to be equal to the integral of x times dA, however we define dA, and y bar is going to be, again, the total area is going to be equal to the integral of y dA. Well, it's convenient for us here because most people, I'm sure, remember that the area of a circle is pi r squared. We have a semicircle, so we know A is 1/2 pi r squared. So we have A taken care of. The real trick to this, though, is defining a dA that's easy to integrate over the boundaries of the semicircle and for which we can relate integrable variables, so our variables that we're going to integrate over, with whatever defines the y position at any given point. So we're going to use a differential element again that is a little square basically that's defined as an arc, rd theta. So it's kind of a curvy square, but it's going to be a square when we shrink everything down in the differential, and then it's going to have a side equal to dr. So it's going to be a little bit of the circle that has a side that's dr, and then another corresponding side that's rd theta. So that's an approximate little square. And so we're going to add up those squares from 0 to our total r, and then we're going to wrap, that's going to give us a little pie shape, kind of a little strip. Then we're going to add up all those strips like a pinwheel all the way around our theta boundaries. So that'll give us our continuous variable expression for dA. So now we need to define any y point in terms of r and theta, because we've kind of defined our dA in terms of r and theta, which kind of makes sense because we're obviously in a circle, so polar coordinates made some sense here for our area element. Well, gosh, this is easy. We can use some trig. So I can say, say I'm looking for the y coordinate right here where my little hand cursor is. Well, that's easy. I can define a radius from the origin out to this point and take sine theta, wherever that theta is. For this theta, or that theta. Doesn't matter. Works for any theta. Trig still works. So easy substitution. My y position for my integral for my centroid is r sine theta, and dA is equal to r d theta dr. So I put that together in the integral. So I have r sine theta times r d theta dr. And I'm going to do the same kind of thing. I'm going to group variables, and I'm going to integrate first with respect to theta, and then, I end up grouping it. So I'll first integrate with respect to r, and then with respect to theta, holding the other variables constant. My rules of integration for multiple variables. And I need to know my limits. So I'm going to integrate r from 0 to big R, which defines the radius of the whole semicircle. And I'm going to integrate theta from 0 to pi, because I'm only integrating a half circle, not the full circle. Okay, so off I go. I collect terms. So first I'm going to integrate with respect to r. Well, sine theta is a constant. Might as well be 5 or 4 or 42. So I'm just going to integrate r squared, and I'm going to get 1/3 r to the third integrated from 0 to r, and that's just going to give me 1/3 r to the third. So this is now a constant because big R is a single number. So that can come out of the integral, leaving just integrating sine theta with respect to theta from 0 to pi. So the integral of sine theta is negative cosine theta. Remember the negative sign, because the derivative of cosine theta is negative sine theta, so we need a negative sign to make the integral correct. And so then when we plop in our limits of integration, we end up adding up to something other than 0. So negative cosine of pi is equal to negative of -1 or 1, and the negative of cosine theta is -1, and so we end up adding up and getting 2. So this ends up becoming 2, and then we had the 1/3 r to the third out front. So we would end up getting a 2/3 r to the third for this part of the expression. Our area was pi over 2 r squared. So we just do some division, and we can write our y centroid is 4/3 big R over pi. So if we think about pi being a little over 3, 4/9, just shy of halfway, maybe a bit shy of halfway. So our y centroid is coming in right around here, which makes sense. We would definitely expect it to be less than 1/2 R. X centroid's even easier. We can do that by observation. It's 0. Or we could go through the integral if we really wanted to. And in this case, the only thing different would be that our x position would be defined by cosine theta. So if you want to do that, feel free. You'll get a 0. Okay, we can expand the same idea to 3D and get z centroids of axisymmetric types of volumes like a hemisphere or a cone. And the trick that you'll see that's going to be true of any centroid or center of mass calculation is finding the dA or the dV in terms of something that you want to integrate. So it's finding that convenient area or volume element for integration. That's really kind of the heart of the matter. And then typically relating your x, y, or z variable to the variables for which you've defined your volume or area element. So if you're used to related rates problems in calculus, this will feel kind of similar, that you're looking for those common variables that you're going to integrate over. In related rates, you probably took derivatives, but it's the same thing. You're looking for those common relationships between your variables that in this case denote the shape, right? Because we're integrating over variables that give us our geometry. So if we have a hemisphere, we're going to, and we want to get the z centroid of the hemisphere. Hint, hint, the x and y are pretty intuitively obvious as 0 again. Z is kind of the trick. We know it's probably going to be less than 1/2 of the radius of the hemisphere, and please apologies for the real sketchy hemisphere here, but we do have a hemisphere that's kind of like a sphere cut off with the equator of the original sphere being on the z = 0 plane. And we have a total radius of big R again. So this is kind of the 3D revolve around the z-axis of our semicircle. So we can define the centroid as the total volume of the hemisphere times the z-centroid equal to the integral of z dv. So we want a convenient dv. The easiest one is a slice, a circular slice. You know, thinking in terms of latitude, a little slice that's a circle with a thickness that's going to be related to the zy or zx function that defines what will effectively be a circle in either one of those planes. And that's our related rate. That's kind of the linchpin that makes the dv work with the z position. So my dv is literally the area of any one of these circles times its thickness. Again, it's a slice, so it's an area times the thickness that gives it a volume, so it's a differential volume. And so now I need to relate the area of any one of these circles to its z position. So obviously it's shrinking. So the bigger the z, the smaller the circle. So I know what that function is though. It's pi r squared, where I'm defining r in a plane parallel to the xy plane. So r is the radius of the circle here. Well, r is related to z based on the function for any one of what would be the longitudinal circles. So I can say that r of the circle that defines my horizontal slice is going to be big R, the radius of the whole sphere, minus z squared, which is itself the formula for a circle. The whole thing's, you can just slice, it's a sphere, you can slice it anywhere and get a circle. So we're getting this particular circle. So if I square this and multiply by pi, I have my A circle. And then I multiply by a dz and I have my volume element. So now I have my volume element expressed in terms of z, which is what I need to put in this function when I integrate. So I can get my total volume kind of the cheating way. I could do 4/3 pi r cubed divided by 2, which I've done here in advance, or I could integrate. I could basically integrate dv over r from 0 to r, and so I could get it that way. But I'll take the shortcut and do 4/6 pi r cubed, and then just evaluate my integral with my z dv, which is equal to z times parentheses r squared minus z squared. I throw my pi out in front because it's a constant. Dz is a single integral. So all I have to do is integrate this expression with respect to z, and it's just a polynomial. So standard integration, and I'm going to integrate r from 0 out to big R. I don't have to worry about my limits in any other direction, because effectively by defining the circle and its area with respect to z, I've taken care of all the other limits. So it's like I've already done my rho phi limits if I were thinking about spherical or polar coordinates, and now I'm just integrating with respect to r. So I've basically evaluated the other if I could imagine this as being a triple integral, I've kind of already done the other two integration operations by creating this A circle and defining its limits in terms of z. So I just had to do the z part, if you're thinking about it that way. So I just crank through the math, integral of a polynomial, and I end up with pi over 4 r to the 4th. And then I divide by my the area of half of a sphere, and I end up with the z centroid at 3/8 times the radius, so it's less than 1/2, just like we expected. Now, something else to remember as you're going through these, centroids are always going to be positions. So if you end up with a centroid with a length squared or a length to the 1/2, you've made a mistake somewhere. You're always going to be looking at getting centroids in terms of just length. So that's another handy check. It's very, very similar operation if we wanted to find the centroid of a cone. This is a right circular cone, so I'm not going to step through everything other than to say that our volume element is defined the same way, and the relationship between the area of our circle and its z position is even simpler. It's just a line function which defines the profile of the cone. So you can again follow the same pattern and get the, in this case, because the cone is oriented with the pointy end down, your z centroid is about 3/4, it's exactly 3/4 of the way up. If we were to have defined the cone upside down, this function would be different, and it would end up driving the integral to give us a 1/4 h. So we would have ended up, we wouldn't have had to worry, we would have gotten the correct answer, but it would have come out of this function, this line having a different slope going the other way. Okay, so that's a good practice problem. All right, method of composite parts. This is the last big concept that we'll cover for centroid. And this is very, very powerful. This turns a calculus problem, which is fine. We're not afraid of doing calculus, but it takes some time. You've got to define your limits, you've got to define volumes or area elements, and then you have to do all the integration right. There's a lot of opportunities for mistakes. If you have simple areas or simple volumes that are well defined and whose centroids are well known, we can use a fundamental property of integrals to turn a calculus problem into an algebra problem. May still be plenty of room to make mistakes if you don't, if you don't add things up right, but it does make things a little bit simpler. And if you have simple shapes, it can allow you to find centroids, especially for things with uniform density, really, really fast. So I'll walk through the proof first, because if you understand where this comes from, you'll never forget it. So say you have two areas, A1 and A2, and they sum up to area total. And we can define the centroid of the total area. That's the same way we would define the centroid of anything else, right? Total area times we'll just think about the x centroid for now. The y and the z would be, or the y would be analogous. So area total times the x centroid equals the integral over everything. So that's the integral over the entire region defining area 1 and area 2 times x dA. And so again, R is, we're going to define the total region of area 1 plus area 2. Okay, well, if A total is equal to A1 plus A2, we can write the left-hand side of our centroid expression as the centroid of the total area is multiplying, rather than A total, we can just say A1 plus A2. Then we can use a property of integrals that says the integral of the sum is equal to the sum of the integrals. Fundamental property of integration. So if the integral over a region that extends over A1 plus A2 it can be written this way, I can break that up into an integral with the same integrand over just region corresponding to A1 plus an integral that integrates over a region that's specific to A2. So this is the sum of the integrals. Okay, well, wait a minute. This just so happens to be sort of the right-hand side of the centroid definition if I were only looking at area 1. So if I'm just integrating over a region that corresponds to area 1, this is equal to area 1 times its own x centroid. So I could say this entire integral is equal to the centroid of just area 1 times the area of area 1, and the same thing with area 2. So another way of saying this is the centroid of the total composite area times the total area is equal to the centroid of one of the parts times the area of that one part plus the centroid of another part times the area of that part. So if we have a simple shape, we can say the centroid of that shape is equal to the centroid of maybe another simple shape, subtract them, and get the area of maybe a complex difference that we wouldn't have wanted to integrate. Or vice versa, if we have a whole bunch of simple shapes with easy to find centroids versus some coordinate system, all we have to do is multiply those areas times those simple, maybe by observation, individual centroids, add up the products, divide by the total area, boom. We have the x or y centroid of what otherwise would have been something that's way more complex to integrate than we wanted. So as an example, we have like a channel, and we want to know what the centroid is in the x direction. So basically we've set up the y vertical on the page and the x in this direction. We want to find both the x and y centroids. So we're going to break this up into 3 regions. We've got horizontal region number 1, horizontal region on the bottom, which we're calling number 3, and then that vertical component, which we're calling number 2. So the area of 1, just using our dimensions, is 1/2 times 3, so 1.75 square inches. Area 2 is going to be 5 inches by 1/2 inch, because we're cutting off 1/2 inch on the top and the bottom, so that's 2.5, total area of 6 square inches. The x centroid of the top and the bottom of part 1, region 1 and region 3 is right in the middle. So if it's 3.5 inches from here to here, right in the middle would be the x centroid. We're assuming it's uniform density, 1.75. Its y centroid relative to the coordinate system, okay, not to itself, because we have to index all of these to a single coordinate system. So the y centroid of part 1 right here is at 5.75 inches. Just remember, from here to here is 6 inches, so we're going to take half of part 1. Its centroid is halfway through itself, which is sitting at a distance of 5.75 inches from our y equals 0 point, which is right along the bottom of part 3. We use the same procedure to designate the y centroid of the upright, which is right in the middle of itself, which is right in the middle of the coordinate system, 3 inches. And then the y centroid of part number 3 is just halfway up part number 3, which is at absolute coordinate 1/4 inch. So then we apply our method of composite parts for both the x and the y direction. So our total area, which is 6 square inches, times our x centroid, whatever it may be, is going to be the sum of the total areas of each of those parts. So we'll have the 1.75 inches times 1.75 x centroid for parts 1 and 3, and then 2.5 inches times 0.25 for part 2. Add them all up, divide by 6 inches, and I get my x centroid for the total, for the whole channel, at 1 1/8 inch. So it's coming in right about there, which isn't surprising because with part 2 being all up against the x-axis more or less, we've got the majority of our area being kind of skewed to the left. And we can get the same thing for the y. We could probably also do the y by observation, but we could multiply it all out and verify that it's indeed at 3 inches as expected. Another powerful technique, which I kind of verbalized, is what we call the subtractive method. So we can basically use this same equation and say we can get any one of the parts by taking the whole, if it happens to be easier, and then subtracting. So an example of that would be to say I wanted the x centroid of again of my channel. I could define a whole square, the single hatched large rectangle, as a total, and that would be 3.5 inches by 6 inches, and it would have, say, its x centroid at 1.75, and then so that would be this term, the whole big square, and then I could subtract the interior, which is sum of everything else in there, and then get the centroid for what's remaining. So the centroid of this part will be skewed a little bit over to the right from the greater whole. So basically you can subtract to get parts as well. So it's totally analogous procedure. So this takes practice, and I would say the biggest mistake that people make is forgetting to reference everything to a single coordinate system. You have to, for instance, if you were talking about this a small part up here, its y centroid is referenced to y equals 0, not to itself. So that's the biggest mistake. If you avoid that, it's very, very straightforward and just takes a little bit of practice to get used to. If you see a centroid or center of mass for a uniform density problem on an exam or a homework, and you can use the method of composite parts, it's probably your fastest and most reliable way of finding it. If you're uncertain that it's going to work, you can always drop back and integrate. Use the fundamental definition of centroid to get it. The one place composite parts will break down is if you have a gradient density and you're looking for center of mass. Generally speaking, if you have gradient density, you're going to need an integral to find. But if you have a density that's discrete, for instance, if you had, say, we're going back to this, if you knew the density of this one part 1 and it had a sharp boundary, you literally had something made of 3 different parts, each one which had a different density, then you could just simply multiply by that density within the method of composite parts. And extrapolate the definition of center of mass and use it directly. But before we do that, let's define center of mass and just make sure we know what we're talking about. Center of mass is defined exactly the same way centroid is, but instead of looking at a line element or an area element or a volume element, we are looking at a mass element. So again, looking at our coordinate system in space, we have C on some body and a radius from our origin to point C, and this time instead of having a volume element or an area element, we have a mass element. So we have the mass of the entire body equaling the radius to any mass point, dm. What's the difference between dm and dv? The density function. So effectively, your center of mass is going to be defined exactly like your centroid, with the exception that you are multiplying by some density function that will be related probably to x, y, or z. It might vary in one direction too, or all three at the same time. So it basically just adds one more function. So instead of just q, you have q times density to give m, and instead of dq, you have dq times density to give d little m. So in this would be the procedure you'd use if you had a continuously varying density. If you had discrete density parts, like a steel part welded to an aluminum part, you could use method of composite parts, using each part's specific density to define its own center of mass and then add up the center of masses. If you have something with gradient density, for those of you who are in composite design, if you were using some kind of metal particle filler or some kind of ceramic fiber, and you had a gradient distribution of those reinforcers, and you were looking for a center of mass, you would probably want to integrate to get that effect over however it was varied. For instance, maybe you have more on an outer circumference of a beam or a rod to give it better moment resistance, for instance. You would then be looking at maybe having a higher density closer to the max tensile axis, depending on what you used. Anyone who's familiar with soils and compaction will know that quite often you'll get gradient density if you have settling or differential void volume in soils. So that's another place that you might use a gradient density function. All kinds of things can lead to different densities. The nice thing is it's just one more function to add to the integral, and it can really shift what ends up being your center of mass point off what it would be from the geometric centroid. So just remember, it's a whole nother perturbation, but you would need to know it to integrate it. You would need to know what it is as a function of x or y or z, and so that would require a little bit of understanding of the physics that created the density gradient, or having somebody just give you a function. Hey, density of this part varies directly with the radius. Easy peasy. Just throw it in. Density equals blah 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 r, and away you go. In that case, you would expect your centroid to be closer out to the edge of something. Okay, this is the end of our centroid and center of mass lecture. I have one more plan to just give a little bit of tip on integration, and it'll be a segue into any kind of numerical method you'd want to use for that. But with that little addendum lecture that's coming next, this will be the last of our topics for this course. So at this point, practice. Again, this is going to feel a lot like what you're probably doing in integral calculus. It should. If it doesn't, that's a problem. So feel free to refer to your math textbooks to get a flavor for this. But otherwise, just please follow the definitions of centroid and center of mass, define those volume elements or area elements, understand what your limits are, and just use the basic definition and make sure your units match. We'll see you next for the addendum lecture, and then that will be it for the quarter. Thank you.